Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by the Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar lecture theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Welcome friends. We will continue to discuss the contents of the SwayamPrabha course titled Maritime Structures, Types, Construction, Pre-Service Analysis and Design, offered by the Department of Maritime Engineering at IIT Gandhinagar. Friends, we have learned so far different types of offshore structures and we said how these offshore structures are part and parcel of maritime structures. We learnt about the variation in their geometric design with respect to the depth of installation. We have also set a few examples of real-time structures which have been commissioned at various parts of the world. We realized the commercial importance, the strategic value of these kinds of structures in terms of national economy. Now we tend to understand the structural design of these types of structures. In general, engineering design is possible only for those systems whose behavior can be predicted. On the other hand, we need to understand the structural response of the system under the given forces acting externally on the system. So now let us ask a question. What are the possible forces that can act on maritime structures externally? So, welcome to this lecture on lecture 4. Lecture 4, where we are going to talk about the structural action of these kinds of structures. Friends, let us try to understand what are the external forces that act on maritime structures. We can list them very quickly. One, predominantly is the wave load. Secondly, wind load. Thirdly, load arising from current, which can be converted to equivalent wave load, which we will see later in the hydrodynamic part of the lecture. In addition, we also have forces which is arising from seismic activities, earthquakes, or otherwise we call as sea quakes. There can be forces arising from accidents, which we call as impact loads. There can be forces caused by fire and explosion. In addition, we will also have forces which is caused by the dead load, the live load, the loads from the machinery operating on the maritime system, etc. So, one can see there is a large number of external forces acting on the marine structural system. So, now based upon a combination of these forces, based upon the time and frequency of occurrence of these forces, they will cause different impact on the maritime structures. So, in this lecture, we are interested to see what will be the structural action otherwise what we call as response of the structure. Friends, let us try to recollect what are the different geometric forms we understood in the last few lectures. We said if the water depth is increasing with respect to the sea level, if the water depth keeps on changing as the seabed configuration is not horizontal, the type of offshore structure recommended to be commissioned in these water depths are not same. We also said the part of the structure below water is what we call as substructure, and the part of structure above water we call as superstructure, and we realize that superstructure is mostly common and similar in all types of offshore platforms, but the substructure varies with respect to the depth at which they are commissioned. Obviously, this will affect the change in the geometric form of the structure. So, when there is a change in the geometric form of the structure, the structural action caused as a response of the structure will also be different. So, what we do now is will take up each platform type one by one, apply the axial forces and the external actions onto the system and see how actually they respond. Most importantly friends, when a structural system gives response, there can be two aspects of this. One, it can respond based on its strength, which essentially comes from material with which it is constructed and the geometric form with which it is constructed. Secondly, it can also encounter the response by undergoing large displacements. In fact, displacement will be a term related to structural response in plane. We will call them as motion. So, if you recollect the term related to this specific concept in offshore design, I would be happy that you can understand that we refer this to compliance structures. Compliancy refers to flexibility. So, now the structural system can be either encountering the forces based on its strength, which we call essentially as a rigid or a stiff system. It can also encounter the response of external loads based on its geometry. We call this as flexible system. So, flexible systems essentially encounter the loads based on its geometric form. Therefore, we call this as form dominant design. So, in a flexible system which undergoes large displacements, other than resisting the external forces, one important concept required in the design is recentering, which we discussed in the last lecture. Let us recollect what do we understand by recentering. We will compare this with elasticity for our reference. Elasticity can be easily understood by an example of a bar or by a rubber band. You can pull this rubber band, the rubber band will elongate. When you release these forces, the rubber band will come back to the same position. So, we can now say the rubber band is remaining elastic. It means it is regaining its shape and size upon removal of load. We call this as elastic property, whereas recentering is comparable to this, but it is in the presence of load. So, if the structural system is capable to return to its equilibrium position in the presence of load, then we call this as recentering. Now, one can compare these two very quickly in a very simple terms. Let us compare elasticity with recentering with a better understanding. Elasticity is a material property, whereas recentering is a geometric property. Elasticity is always assessed based on removal or absence of load, correct? Whereas recentering is always checked in the presence of load. Elasticity is important for all structures and materials. Recentering is important only for flexible or compliant systems. So, now one can see the corollary of this slide with the previous one. So, both slides are comparing elasticity with recentering, correct? But this slide tells me a general information about the property. This slide tells me the application of information about the property. Okay, I think it is very clear. Why we are making an emphasis on this is, based on this understanding, we will now explain the structural action offered by different structural systems under external load actions. Okay. Let us also ask another question. What are the different kinds of platforms, types of platforms we have learnt? I will put them a list here. You will tell me how they are grouped. One, I would say fixed platform. Then I would say compliant platform. Then I would say completely floating platform. I have not discussed so far the new generation platform. We will discuss that later. Floating platform. The examples of a fixed platform could be a jacket platform, a gravity based platform, and GBS and jacket platform. This is also called as a template structure. And examples of compliant systems could be jack up rigs, tension leg platforms, guide towers, articulated towers, and single point anchor reservoir. An example of floating platforms could be FPSO, floating, production, storage and offloading. It can be FSO, it can be drill ship, it can also be a semi-submersible. Now, the structural action of each one of them is different under the external loads. So, let us go one by one. How do they behave? Let us start with a jacket platform as you see in the figure here. So, an example of a jacket platform is what you see as a sketch value, and if you recollect the name of the platform, it is Bullwinkle platform constructed in Gulf of Mexico. So, you can see the top side of this platform, which has got a flat boom, which has got a drilling derrick, which has got a crane, a helipad, living quarters and all electromechanical equipments placed in this deck. Let us see how this platform encounters the lateral loads. Number one, when the wave load is acting on the platform, when the wave load acts on this platform, the platform will resist these loads primarily by its stiffness and strength. So, these platforms do not undergo any motion at all, or the displacement of this platform is very minimum. Can you tell me why? Very simple reason, friends. This platform is actually fixed to the seabed. In fact, a pile is driven for the legs, okay, and this pile will not allow any displacement at these connection points, correct? Therefore, these platforms undergo very little displacement, and hence if at all load has got to be encountered by this platform, it can be only through by the stiffness and strength of this member or the structure. So, let us look at the wave or the load transfer path. How the load gets transferred? Let us say I have a wind load. Wind load is acting on the platform, let us say in the substructure. The wind load encounters to these legs, and from the leg by its strength it goes to the pile, from the pile it goes to the foundation. Okay? So, the load transfer platform essentially, if it is a wind load, it goes to the deck, from the deck goes to the legs, from the legs goes to the pile. So, from the deck goes to the jacket. These are called jackets. We already discussed why the jackets are transparent in nature. We gave an example of a wind side hoarding on the roadside banners. So, jacket goes to the deck, goes to the jacket, from the jacket goes to the piles, from the piles goes to the seabed. So, this becomes my load transfer path. Now, let us ask a question in engineering perspective. What would be the dominant design force which will govern this platform? Axial forces on the bracing will govern the platform, whereas the legs will encounter a combined action of axial force and bending. So, axial force and bending moment will be the governing factor of design of these kind of structures. What is the use of piles? Piles provide fixity at the seabed, and they will limit the displacements at the seabed. Okay? And very importantly, they are suitable only for shallow waters where the structural rigidity is feasible. The structural action of a fixed platform is very simple. It resists load by strength. Okay? Having said this, let us move to gravity based platform. Let us keep on checking one by one. We talked about the jacket platform. I will just put a tick mark here for our learning. We did this. Now, we are going to talk about the gravity based platform, GBS. We know the term gravity base suggests that the base is a colossal model. It is a huge mass, and immediately we recollect that these structures do not require conventional foundation like piles. They rest on the seabed by their own weight. That is why they are called as gravity base. Okay, one can see very clearly the extended part of this colossal weight, which is huge at the bottom. So, this mass will help the platform to rest, to sit on the seabed by its own weight. So, they are huge, massive structures. The self weight of the structure is very high. Essentially, these kind of structures are constructed by concrete. In addition, these caissons will also add further weight to the structure. These are called caissons. They will add further weight to the structure. So, on the whole, this system is a massive unit. So, now one can expect that if a wind load or a wave load acts on the platform in the superstructure or substructure, how they will be resisted? Yeah, they will be resisted by the base friction. In simple terms, if I have a member having a huge base at the bottom and it is resting on the seabed, if I apply a force to the member, the resistance will come from the friction offered at the base. So, they resist forces by base friction, and also they have a very large overturning resistance. What is an overturning resistance? Let us talk about the same figure, and if you want to take a moment, let us say about this point xx. The moment about this point xx will be the reaction offered by the safe bearing capacity of the soil of this whole area, which is very high, and the Cg of this force multiplied with the lever arm will give me the moment of resistance, correct. So, this offers a huge overturning resistance because the weight acting on the platform, which is equal to this, is very high. So, they offer huge overturning resistance and base friction. So, the lateral load acting on the platform is resisted by two components. One is the base friction, other is the overturning resistance. Now, let us see how the load path gets activated. When the load is acting on the system, it passes through the body and activates the contact pressure at the seabed. Friends, it is very important that the foundation or the soil mechanic characteristics should be able to offer this pressure in the upward direction. So, this kind of platforms may not be suitable for all types of soil. Soil should be able to offer resistance from its bearing capacity. There are certain grades of soil which do not offer enough bearing capacity. So, this kind of structures are not feasible to be provided on those kinds of soil as well as on rocky surfaces. There is one great issue with this kind of platform. What is it called? Seabed covering. So, let us look at this example again. We are talking about the water level somewhere here. This is water level, this is my top side, okay. It is a seabed, Since the mass is very high, it starts covering the seabed. So, when a huge mass is supplied onto the system, this starts giving you covering of the seabed. So, this system will gradually get sponged into the seabed, and this will displace the soil from this part out of the surface. We call this as seabed covering. This is a very serious issue as far as these platforms are concerned. So, this can be anyway addressed by strengthening the subgrade material of the seabed. So, seabed covering is one important issue which we have in this kind of platform, and here further the structural action confirms rigidity and non-compliancy. Okay? So, it is resisting force by its rigidity. Now, let us go back and check gravity based structure and jacket platform. Let us move on to the next type of platform, which is a jack-up rig. When we talk about jack-up rigs, as you see in the picture, jack-up rigs are founded to soil using something called spud cans. So, spud cans offer a hinged connection at the bottom, which will make the connection rigid in the vertical direction, but it offers moment capacity at the bottom. So, it is a hinged connection which does not resist any rotation, but it offers resistance only in the vertical direction. So, spud cans will help you to offer this kind of resistance, which are a foundation for jack-up legs. So, when a platform of jack-up rig is installed in a specific site in a sea state, the vertical loads acting on them will be transferred to the deck. From the deck, they will go through the legs. That is a transfer path. From the legs, SPUTCAN will offer vertical resistance to these and they will be resisted. Okay. So, the structure is again remaining stiff with a minimal motion and suitable for moderate water depths only. When a SPUTCAN is located in position, the loads are applied and resisted by the vertical reaction offered by the SPUTCAN. So, jack-up bricks undergo very minimal motion and they resist lateral loads and gravity loads by their stiffness again. So, let us go back and do the checklist that we have learned how the load transfer mechanism happens in jack-up bricks, which is also a part of fixed platform, but I will not call fixed because the support is not completely fixed because of the hinged connection offered by the SPUTCAN. Let us go to the next kind of platform, which is a compliant tower. It can be a guide tower, it can be articulated tower. For both of them, the structural action is more or less same. Let us recollect about this particular type of platform. So, these platforms are actually constructed by a top side which is essentially a truss model system, and they are also again founded using a SPUTCAN. Let us mark the water level somewhere here. So, they will offer something called a hinged connection here. These are like hinges. So, let us mark them as a line diagram. When the wave is acting on the platform will start oscillating above the pendulum point like an inverted pendulum. Okay. Now, this motion or this rotation is the compliancy, it is the flexibility. So, the platform is started moving, dancing above this point. This compliancy is going to now help me to resist the loads. How can you do? One can say that when the load is acting in this direction, the platform will move to the right. Therefore, the relative load which is between the contact point and the point of displacement are different. So, this relative motion with respect to the water particle and the system are different, and this motion helps me to reduce the load or to counteract the load. So, the structural action of this platform is by motion. So, one can say the restoring forces comes from the guy wires or teethers or mooring lines, whereas the response of the system is offered by its flexibility and geometry. So, as you know, in a guide tower, we have something called guy wires. Wherever the guy wire is connected to the structure, we call this as a fair lead. Wherever touching the seabed, it is called as a touchdown point. This guy wire, when the platform moves to the left, will try to pull this back. When the platform moves to the right, this guy wire will try to pull the platform back, and the recentering is offered by these guy wires. So, we say that restoration or recentering is happening by the guy wires or tethers or mooring, whereas the load resistance is offering or offered by flexibility or motion of the platform, which enables from the geometric structure of the platform. So, therefore, this platform is extended to deep waters and ultra deep waters. So, the examples of these platforms could be an articulated tower. We call this as an universal joint, which is also called as articulation. This is similar to what you have a ball and socket joint in your wrist arm, in your shoulders, etc. It is an example. Okay, this is a universal joint. Okay, similar to this. So, they have a capability to recentering them. And we explained in the last lecture that how the buoyancy chamber helps to restore the position of the platform and how the ballast chamber helps to improve stability of the platform. So, the environmental loads acting on the platform are counteracted by the pendulum action of this structure. So, the structural system now resists the forces by its motion, okay, because it is a compliant platform. Let us move on to the next platform, which is tension leg platform. For a tension leg platform, we understood that the basic design philosophy is buoyancy exceeds the weight. Let us draw a TLP. So, these are the tethers. I am drawing them in red color. They are fixed to the seabed. This becomes my water level. We call this as draft dr, and of course, this is our water depth. These are tethers, otherwise called as tendons. Okay. We already heard yesterday about TLP mechanics. When a wave encounters the platform moves to the right with the tethers connected to the same point. This movement is called offset and this movement is called set down. We already saw that set down is much lesser compared to offset. So, the platform now undergoes a relative motion, right? It keeps on moving this way or this way, and this compliancy helps to counteract the forces acting on the platform. Now, how the platform recenters? Let us say these are all axially loaded tethers. When the platform moves to the right, the horizontal component of this tether or the force, let us say the axial force in the tether is T naught, and if this angle is gamma, one can find the horizontal component of this T naught, and that will be significantly larger, okay, significantly larger. He will try to pull the platform back to equilibrium position. On the other hand, if the TLP moves to the left, the tethers will try to pull the back platform to its equilibrium position. So, the recentering is happening because of the tethers action and the load transfer is happening because of compliancy action. We call this as TLP mechanics. Having said this, let us see how a spar platform counteracts the forces. Let us go back to the checklist and see, have we covered all types of platforms? So, we have seen the tension leg platform, we have seen guide towers, we have seen articulate towers. Now, we are checking with a spar platform. Okay, let us go back to spar platform and try to understand how the spar platform encounters the loads acting on the structure. What is the fundamental difference between a spar platform and other complaint structures? Let us say I have a spar platform which I am drawing here, superstructure. Then the substructure is a cylinder, then the wires anchor. Remember this bottom, this is the seabed. And the water level is somewhere here. Okay, this is a superstructure, what we call as the deck of the platform, and this is the hard tank. Now, the depth of immersion of the tank in water is very high. We call this H dash. H dash is approximately about 80% of H. So, we call such systems as deep draft system. What is the advantage of having a deep draft? We know by Archimedes' principle, the buoyancy force offered by any body depends on the submerged volume of that body. So, for the same diameter, if the depth of immersion is larger, so pi d of h prime is very high, and that offers me very high buoyancy, and this buoyancy will help me to resist the weight. So, the buoyancy is counteracted by the weight, and the lateral forces acting on the system is again counteracted by its compliancy. So, the relativity between the motion of the body and the water particle helps me to counteract the lateral forces. The axial forces are counteracted by the deep draft buoyancy force offered by the deep draft of the hard tank. Okay? So, the structural action of a spar essentially depends on the inertia and hydrostatic restoring forces. The mooring system provides station keeping of this platform. Very interesting component of this design would be the natural periods of this platform. The natural periods of this platform are fairly large. They will avoid wave resonance. So, the structural action is dominated by rigid body motion. Okay? That is how the spar platform counteracts the lateral forces. Friends, in the process of this lecture, if you have any doubt, please write down them on a paper, post them in discussion forum, and the instructors of this course, myself and Professor Gaurav and other TAs will be able to help you to make you clear your doubts on 24/7 on the discussion forum of SwayamPrabha. So, whatever questions you have, please post to us or email to us. We will help you to learn and understand the concepts better. Let us move on to the next platform, which is a semi-submersible platform. The word semi-submersible clearly tells me it is a half resting vessel. Let us say if I have a platform of this order, so the bottom members are called as pontoons, the vertical members are called as columns, the horizontal member here is called as a deck, and this deck contains the flare boom, it contains the helipad, it contains the drilling derrick, it contains the living quarters, it also has electromechanical systems, all. The water level is somewhere here. Let me mark the water level. Water level. Okay. So, the size of the platform is so large, approximately 100 meter by 100 meters. The displaced volume could be very high, and that will offer me a buoyancy force which is going to resist the weight of the platform. Okay. Let us see the structural action of this. Semi-submersibles have minimum water plane area and they help us to reduce the wave induced forces. What do you understand by water plane area? The area which encountering water flow is what we call water plane area. So, look at this figure carefully. I have a column here and a column here. In between it is transparent, okay, there is no member. So, we say that this structure has got minimum water plane area, correct. Similarly, I have a pontoon here, I have a pontoon here. In between this area is hollow, empty, water can flow. So, it has got a minimum water plane area that minimizes the wave forces acting on the system. The loads acting on the deck are transferred to the columns and then to the pontoon and then to the mooring system. Platform essentially relies on hydrodynamic transparency. It does not rely on structural stiffness. Friends, look at the variation between structural action of a fixed platform to structural action of a floating platform. A fixed platform essentially dependent on the stiffness and rigidity and strength, whereas the floating platform depends on hydrodynamic transparency offered by the geometric form and not by the stiffness and strength. Furthermore, there is a very strong coupling between the heave and pitch motion of this platform, which we will discuss later in the introduction to dynamic sessions courses of this particular course. The most important concept what we want to emphasize here in the structural action of semi-submersible is the structural fatigue. Structural fatigue caused by reversal of loads can be one of the important reasons for the failure of these platforms. So, these platforms should be investigated for fatigue failure in terms of its strength characteristics. Let us move on to new generation platforms. We talk about triceratops. We have a separate lecture on explaining the concept of triceratop. Let us quickly explain what a triceratop is. Please pay attention. There is a deck on the top and there are buoyant legs at the bottom. The buoyant legs and the deck are not connected integrally. They are separated, they are isolated by a ball joint. So, I keep a ball joint between the legs and the top. What is the purpose of this joint? When the load is acting on the superstructure, this load will not be transferred or the motion will not be transferred to the substructure. When the buoyant legs keep on responding to the wave, this motion will not be transferred to the superstructure. So, the ball joints will partially isolate the rotations to the deck or rotations from the deck to the leg. So, they act as similar to something called seismic isolators. Okay? So, the ball joint isolates partially the superstructure and the substructure, and it has got all components like a crane, a drilling derrick, a flare boom and all electromechanical systems which are normally present in an offshore platform. In addition, friends, as a made in India concept, IIT Madras investigated very interesting concept of using this platform for rocket launching in sea. The seaborne rocket launches will be the first time of its kind in the world if it is expected to happen, which is to be a made in India concept under the Ministry of Earth Sciences or Ministry of Environmental Control. So, it is very interesting that this platform can also be used as a space for rocket launching in sea, because when the rocket is launched from here, this platform will undergo a cantilever action and that will not be transferred to the legs. So, the platform can act independently as a space launch system in sea. There are many advantages of this particular system when it is done in sea. We will discuss them in detail. Now, we look at the structural action of this platform. The structural action solidly depends on the geometry induced compliance and not on rigidity of the platform. Environmental loads are distributed amongst the legs and the teethers. The legs are further connected to the seabed using teethers like a TLP. Therefore, Triceratop is a hybrid combination of TLP and spar, because the deep draft is borrowed from spar, the teether system is borrowed from TLP. So, this borrows TLP concept, this borrows the spar concept. So, put together is Triceratop. It is a new generation platform which is coming up in the recent future for offshore exploration in ultra deep waters. The geometric form reduces the forces acting on the platform and improves its stability. The last kind of platform what we see is a regasification platform used for LNG storage and regasification. The concept is more or less similar to Triceratop. Look at the platform here. It is used for LNG storage. LNG processing is a very complicated chemical process which happens on the deck itself. Usually, when LNG carriers are adopted, they are transferred to the ship, through the ship to the coast, they are processed there. But the cost of this transport is very high. To avoid that, one can also do this on the deck itself. So, again the legs are partially isolated from the deck using ball joints. So, the behavior of structural action of a BLSRP is similar to what we have in a Triceratop. So, friends, let us come to the summary part. In this lecture, we learnt about the structural action of fixed, compliant and floating platforms and new generation. Hope you have followed the lecture. Thank you very much. Namaste.